This is a complimentary video for the research paper with the title The Urban Last Mile Problem: Autonomous Drone Delivery to Your Balcony. As you might know, various multinational companies are already testing their drone delivery services, since drones have several advantages compared to traditional delivery trucks, like quickness, no local emissions, or the possibility of automation, which would require less human labor. But here comes the tricky part. How do you automate a task like drone delivery, which is extremely situation dependent but also safety critical? Well, first of all, you need a drone capable of autonomous navigation. The Intel Aero ready-to-fly drone is a fully assembled quadcopter intended for agile drone application development. It features a compute board with a quad-core processor for high-level processing and a flight controller for stabilization and flight. It also features a front-facing camera capable of three-dimensional depth sensing and a down-facing monochrome camera with global shutter intended for visual odometry. This diagram summarizes the system architecture of our autonomous delivery drone. The application runs on two separate processors. The flight controller contains an embedded processor capable of executing the autopilot, while the rest of the software components, namely visual odometry, trajectory planner, visual marker tracker, and the control logic, are executed on the processor of the compute board. You can find more details about our work in the conference paper. Here you can see the execution of our code in the simulation environment Gazebo. The goal of the mission is to fly to the balcony tagged by the circular visual marker. In the first phase, the drone descends while scanning the building for the marker. Since it flew close to the ground and still didn't find it, it continues scanning to the right and then upwards. On the top right corner you can see the occupancy grid built by the trajectory planner. As soon as the marker is found, the drone approaches it in small steps, using the trajectory planner to avoid collision. The trajectory is visualized by a line, with the position setpoints sent to the flight controller represented as small spheres. The algorithm can also be executed on the real drone. Since GPS position is inaccurate close to buildings, we use visual odometry for localization and navigation. The occupancy grid and the trajectory with the position setpoints are visualized again in the top right corner. You can also see the output of the depth camera in the bottom right corner, where the lightness of the objects correspond with their distance to the camera.